So kind of looking ahead, stuff will be due on block day next week. We're going to do some algebra tricks today. Monday, I hope we may have to remind ourselves some unit circle stuff, limit with trig. More limits on Tuesday. Continuity is related to limits. In fact, it's all limits. So the test is really about limits. All right, so we're going to do some algebra tricks today. 1.3. Limits with algebra. And we'll start with this favorite AP function. That's not really its name, but that's what we're going to call it because they like to use it a lot. Absolute value of x over x. We saw this on one of the worksheets. It had a -2 in there that shifted it. So it's not a hard function to figure out, but if you have it memorized, it'll make your life easier later because it just needs to be one of those parent functions that you know. So if x is positive, if x is 1 or 2 or 3 or 4 or 7, then this ratio is just going to be 1. Can't divide by 0 though, so there's a hole at 0. And if x is negative, then we'd have positive 1 over negative 1, or positive 3 over negative 3, or positive 8 over negative 8. So there's what our picture of that function looks like. And again, it doesn't have a name, but they use it a lot, so you sort of need to add that to your library of parent functions that when I say parabola, hopefully all of you picture the u in your mind. And when I say absolute value, you picture the v. Square root, I mean, there's 5 or 6 parent functions that you know well enough that when I mention it, like your brain, hopefully, can picture it. You need to add this to that list of functions that you know, whose graph you know. Because we can ask questions about that function having to do with its limit. In fact, this is now review because we're looking at a picture. So what's the limit as x approaches 0 from the right? One. And then as x approaches 0 from the left, limit as x approaches 0 from the left, what's that equal to? Yeah, -1. And then if we don't put a left or right on there, if we just say limit as x approaches 0, what's that limit equal to? Does not exist. And why is it D and E? Okay. Yes, you're right. Well, we officially want to say it has different left and right limits. But yeah, it's 2 different places. So there's not really one answer. There's 2 answers, which means there's not an answer. So almost always something about that function shows up, usually just on the multiple choice part of the AP test. But they won't give you the picture, they'll give you the graph, or they'll give you the function, the formula, and ask basically one of those 3 questions. And if you know what the picture looks like, the question's easy. If you're stuck without the picture, you can figure it out, but it's just a lot easier looking at the picture. All right, 3 reasons a limit D and E does not exist. We've seen 2 of these already. I don't know if you remember them, but we've seen them. One of them we just looked at was this different left and right limit, so we'll start with that. Do you remember from yesterday or day before a different reason why a limit doesn't exist? But a limit can exist if there's a hole. So it's not a hole. It goes off to infinity. It goes to infinity or negative infinity. And you really don't even have to specify which one. Like you just mean it goes on forever one way or the other. That means there's not a limit there. And then lastly, we haven't seen this one, and this one's pretty rare, but it's the third one, so we need to know it. And that is if it's oscillating at the x value. This is a little bit tricky. So sine and cosine, they oscillate, but there's limits everywhere, so they're not like weirdly oscillating. What is weirdly oscillating is the sine of 1 over x. Because if we tried to draw that, it oscillates more and more as x goes to 0. It's a really weird looking graph. And so the limit as x approaches 0, there's not one, because it just oscillates more and more. It's not like you could zoom in and find something. Like on a regular sine graph, you could zoom in and see where the point is, but on this thing, at least at 0, it oscillates more and more. And you can kind of see why. 1 divided by 0 doesn't work, and that's sort of what blows up this problem. So the first two are much more frequent. We'll see those all year long. But occasionally that third thing pops up. So it's basically just sine or cosine of 1 over x. Doesn't work. All right, Roman numeral 2, properties of limits. 3 Roman numerals, but 1 and 2 put together are about equal to the third. So if you're trying to pace out how long this is going to be, properties of limits are easy. They make sense. They behave like you think they would behave. So this is usually an easy section and a section of the test that nobody misses anything on, unless they just make a dumb adding mistake or something. So I'm going to give you some limits, and then we'll do some stuff with them. If limit as x approaches 2 of f of x equals 3. So I'm just going to give us some limits to work with. Limit as x approaches 2 of g of x equals -7. So again, these aren't like always true. These are examples that we're going to work with. And let's do one more. Limit as x approaches 2 of h of x equals 0. All right, number 1. Limit as x approaches 2 of f of x plus g of x. We need to put parentheses around f plus g to make sure the limit goes to all of that. Otherwise, the limit would only go to the first thing. So, limit of f plus g. Now, if I told you this was straightforward and there wasn't anything tricky about it, give me a guess. What do you think the answer to this problem is? -4. So, even though this is kind of weird, kind of new stuff, some of the usual rules still apply. So, it's not officially the distributive property of limits, but that's kind of what it is. 3 minus 7 is -4. Number 2, limit as x approaches 2 of 4f of x minus 3g of x. For f of x minus 3g of x. Give it your best guess and you will probably be correct. Alright, someone want to take a stab at it? 33. 4 times 3 is 12. 3 times negative 7 is negative 21. 12 plus 21 is 33. So these limit properties are nice. They act like we think they should act. Limit as x approaches 2 of f of x times g of x. Okay, so we've sort of verified that addition and subtraction work. If there's just a number multiplier, that works like we think it would. What about f times g? What do we think that's going to be? Negative 21. Okay, there's no tricks in properties of limits. There's some things later in calculus where you want to multiply and it doesn't work as nicely as we think it does. But for limits, things work like we think they should. What's that? Not today. Eventually we'll do that kind of stuff. We don't have enough information to do that. We do want to do limit as x approaches 2 of g of x over h of x. So this one's a little bit weird, but it still follows the rules that we're supposed to know. Andrew just says no. And in some way you're right. I don't want you to just write no, because then it feels like you're objecting to the problem. The answer is no. The answer is, a little more officially, it does not exist, because we can't divide by 0. So no is not exactly what we're looking for, but you're correct.
Do you have to have the brackets on it if it's division?
So I don't think you would have to have the brackets on this one, because it's clear that you're taking the limit of that quotient. If we put them on there, it'd be a little extra clear what's going on, but I don't think we would have to have it for that one. I think we would have to have it for all the others. All right, so properties, easy. They work like you think they should work, so you don't have to train your brain or retrain your brain to think about things differently. Just do what you think is right for limits, and you'll be okay. All right, now for the sort of the heart of this lesson. There's some new stuff that maybe doesn't fit what you already know. Some algebraic methods for finding limits. We're going to do 3 methods. The first one is super easy, the next one is kind of easy, and the last one's kind of hard. So the first one is substitution. And yes, that just means plug it in. It is kind of, I shouldn't say it. If x is approaching 2, plug 2 in. Always, always, always try this method first, because a lot of times it gives you the answer and you're done, and it's the easy method. People forget about it because we don't test this method a lot because it's so easy. We test the harder stuff, and then we throw in an easy one, and you end up trying to do something hard and messing up a problem that was really an easy problem. All right, some examples. Limit as x approaches 4 of x squared. Let's take the long way around first. Let's think about the graph of x squared. What's the graph of x squared look like? Yeah, parabola. As x approaches 4 on a parabola, like there's nothing weird happening. There's no asymptotes on a parabola. There's no holes. There's no jumps. There's nothing goofy going on. So I can just substitute 4 in for x. And that's my answer. Remember that sometimes the limit and the function are the same. And this is sort of using that property. If you know by the graph that the limit, there's nothing crazy about any of the limits, that the limit and the function are the same, then you use the function to evaluate the limit. This one's like easier but harder at the same time, if that's possible. Limit as x approaches 2 of 3. So think about the graph of y equals 3. What's that look like? Yeah, good, Andrew. I was worried. You're like this. I'm like, let's rotate it this way. Yeah, it's that horizontal line at 3. So when x is getting closer to 2, what's the function getting closer to? 3, because it's always at 3. Oops, this would be number 3. Limit as x approaches 1 of x squared plus 2x plus 3 all over x minus 2. Okay, well that's a jump in difficulty because I don't know what that graph looks like. I do know there's a problem on that graph. So do you remember from your pre-cal days what the problem with this graph would be? Like what x value would create a problem for this graph? 2. So at 2, something weird is going on. Before factoring, I'm not sure, but I'm guessing a vertical asymptote. But that doesn't matter because we're not at 2, we're at 1. So at 1, there's not an issue, only at 2. So I can use substitution. I couldn't use substitution at 2 because I don't know what's happening at 2, but I'm not worried about 2, I'm worried about 1. So try substitution first. If substitution isn't the right method, you'll know it because you'll get 0 in the denominator. You'll get something weird happening. So try it first. If it blows up, then you got to try something else. But try it first. All right, method 2, factoring. And if you factor, then you substitute. So we're still going to go back to substitution. Limit as x approaches 2, x squared plus x minus 6 all over x minus 2. I guess maybe we should first ask, how do we know that substitution won't work? Like I said, try substitution first. What would be the problem with substitution on this one? You get 0 in the bottom, so something is not right about substitution. So let's do factoring. So limit as x approaches 2. X plus 3 and x minus 2. Well, that was kind of a rigged problem because what happens with the x minus 2's? They cancel. And remember the reason we couldn't substitute because we would get 0 in the bottom. But We don't have that issue anymore. So now we can substitute. Do you remember from pre-cal days what happened on the graph if a factor of the top and the bottom canceled? Remember what that led to on the graph? A hole. And so there's a hole at 2, 5. So the function doesn't exist at 2 because there'd be a 0 in the bottom. And the graph doesn't exist at 2 because you can't divide by 0. But the limit does because it's just a hole. So I should be hesitant. I don't know what the graph looks like, but at 2, 5, there's a hole there. All right, let's do one more factoring and then we'll jump into the deep end. Limit as x approaches negative 1 of x cubed plus 1 over x plus 1. Again, you can try substitution first. It's not going to work because you get 0 in the bottom. You also get 0 in the top. So let's see if we remember how to factor x cubed plus 1. Sort of the hidden reason for working this problem. Do you remember how to factor a sum of cubes? Or the saying that goes with it? Oh yeah, 2 terms and then 3 terms. Something about always positive there at the end. SOAP. So same sign, opposite sign, always positive. Yes. What goes in the blanks here? Do you remember? First one's x, and then 1. Does anybody besides Emma know where those numbers came from? So you cube root the 2 pieces to get the first 2 numbers, and then it's square the first one, multiply the 2 together, square the second one. All right, now let's back up or fast forward out of algebra back to calculus. Again, we got something that'll cancel, which is good because the problem was the denominator. Now it's gone. Now we can substitute negative 1. Lots of negatives to be careful about there. Square of negative 1 plus 1 plus 1 would be 3. So the limit exists even though the function doesn't because there's a hole there. All right, last little subsection here. Oh yeah, we got time. We're good. Rationalize. Do you remember where you used the word rationalize and what situation that was in when you rationalize something? What's that?
Like rationalize the denominator for the square root.
Good. Rationalize the denominator if it was the square root. So, like if you had 2 over square root of 3, right? You would rationalize the denominator by multiplying top and bottom by square root of 3. All right, so 2 root 3 over 3 is the same thing as 2 divided by root 3. It just looks nicer. We're going to use something really similar to that Today we're going to rationalize the numerator, which probably feels odd because up until now the only thing you ever rationalized was the denominator, because some reason long ago someone decided they didn't like radicals in the bottom, so you had to fix them. Now we're going to fix them when they're in the top. The good news is it works kind of the same way as rationalizing the denominator, so you've at least got some experience with this type of problem. Limit as x approaches 3 of the square root of x plus 1 minus 2 all over x minus 3. Well, we always said to try substitution first. What would happen if we try substitution? Yep, we'd get 0 in the bottom. What would we get in the top? We'd get 0. If you get 0 over 0, that means you've got a pretty good candidate for an algebra fix. You can't cancel 0 over 0, but it means there may be something going on where we can fix this. So let's rationalize the numerator. Now, it works the same way as it did in pre-cal. So do you know, or can you guess what you would multiply the top by to fix it? You're on the right track, square root of x plus 1, but that's not all. If we multiplied by just that, it would fix this piece, but it would mess up the minus 2. Plus 2. You might remember that's called the conjugate. You don't really care what it's called, but when you multiply by the minus plus thing, it ends up fixing it. And of course, whatever we multiply to the top, we better multiply to the bottom. So limit as x approaches 3. Let's FOIL the top. So first times first. Well, what's the square root of x plus 1 times the square root of x plus 1? X plus 1. And then the outside would be 2 square root x plus 1. The inside is going to be minus 2 square root x plus 1. That's good news. That always happens when we multiply by a conjugate. Those will cancel. And then last will be 2 times 2 is 4. In the bottom, it might be tempting to distribute, but don't distribute the bottom. Leave it as is, and we'll see why in just a minute. So just leave the bottom set up to multiply, but don't distribute. All right, let's clean up the top here. We already said those would reduce or cancel. That will always happen if you multiply correctly. So what's left in the top? X minus 3. And in the bottom, x minus 3 times that other stuff. Algebra tricks. Well, what do we get to do now, though? We can cancel the x minus 3's, and that means we won't get a 0 in the bottom when we plug 3 in. So I'm still going to substitute, but I'm going to get something that works now. So 3 plus 1 is 4, square root of that is 2, plus 2 is 4. And then I don't think I've seen this error in calculus, but in younger grades, occasionally students will leave that as their answer, which is kind of humorous to me anyway. What's missing there? The 1. Right? But you see what they did, like, oh, the x minus 3 canceled, so there's nothing in the top. Like, well, not exactly how it works. Alright, let's do one more of those, but maybe we'll just pick one from the assignment. There's only 2 in the assignment, though. So, I want you to have both of those practices. Do you want to see another example of this? Okay. Limit as x approaches 0, square root of 2 plus x minus square root of 2 all over x. This one will go a little faster because we know what's going on here. So if I plug in 0, I get 0 over 0. So if something's going on with this thing, let's fix it. Square root of 2 plus x plus square root of 2. Again, leave the bottom alone. That's the mistake that people make. They multiply out the bottom, and then stuff won't cancel, and then they're still stuck getting 0. Leave the bottom alone. Right in the top, whoops, square root goes away. That's the whole point. So just 2 plus x. And then what happens to the O and the I of FOIL? They cancel. So if you're comfortable not writing them out, that's fine. Like, the whole point is to make them go away. So if you don't want to write them out, that's fine. And then the last would be minus 2. In the interest of time, I'm not going to rewrite the bottom. The top, let's see, the 2 minus 2 goes away. The x's cancel. And now we can substitute without having a 0 in the bottom. And we'll talk more about what calculus calls safe stops. You don't have to simplify your answer nearly as much in calculus as you did in previous math classes. If the work that's left is not calculus, you can leave it. And so I'm going to leave that as an answer. Just to practice, it's 2 root 2, but I don't have to do that. I can leave that as my answer. We'll talk a lot more about safe stops as the year goes on. Basically, you don't have to simplify everything you had to simplify in previous math classes. Not by a long shot. So page 67, 5 through 25, 37 to 55, odd. Notes were long, but only 2 of those are the long fix the square root problems. The rest are like properties of limits, some of the easier stuff. So it's a lot of problems, but it goes pretty quick. The answers are in Calc Chat. Oh, maybe I should remind us that this is section 1.3. So if you want to use Calc Chat, 1.3. And the workbook, or the picture of the book, is posted in Schoology. So you can find everything you need online.